So this is the video review for exam 1, and the first problem is a acceleration problem like we did basically first day of the class, where we were looking at accelerations. In this case it was a function of s. Many people assumed that it was constant acceleration, and constant acceleration means that a is a number. It is not have any kind of variables in it, but if a is a function of t, or a function of velocity, or a function of position, then it's not constant acceleration, and you cannot use the constant acceleration assumptions and equations. So the second thing is finding out how far it goes, and that was just a little bit of curve kind of problem, and that's what the 677 was all about. So to set up the problem, what we're looking for is the speed here. You set that up as an ADS is equal to BdV. You have to integrate it, and you get 73.48. So the common mistakes were recognizing that it's an ADS is equal to BdV problem instead of a constant acceleration problem. Many people messed up the distance, and a lot of people messed up the integration. So those are obviously things that we went over in class or in homework that were similar to that. All right, the second problem is a projectile motion problem, and there were two versions of this problem. The first one said that it takes 1.6 seconds to get to the wall, and you had to figure out what that angle was. So you set this up just exactly like we've done before. Do the x's over there, the y's over there, find out what that angle is. We knew what the time was. You plug those into the y equation, and you find out the height is 16.7 feet. And again, the height here is going to be that ending y. The beginning y was at 5. If you happen to have the second version, which was given the angle and you didn't know the time, you set it up again exactly the same way, with the x's over here, the y's over here. X is equal to v cosine theta times time. Here you plug the angle in and find out the time. You plug the angle and the time over into the y equation, and you get height is equal to 15.85 feet. This third problem, there were two versions of this as well. Here we were looking for, the first version was if the coefficient of friction is 0.5, how fast does it need to go before you slide off? Both versions of the problem are set up exactly the same, where you recognize that there's a tangential acceleration and a normal acceleration. And if you draw it face down looking at there, then there'll be a normal acceleration and a tangential acceleration. And remember what we did before, and you did a homework problem just exactly like this, is that where it slides off is where the friction is exceeded. The friction is a combination of the force in the normal direction and the force in the tangential direction, so we call that force total. Remember again, the acceleration is caused by a force in the normal direction. The tangential acceleration is caused by a tangential force, and again, the square root of the sum of the squares is the total force. So just recognizing that, and we see that A tan is 1.5. The normal force is mv squared over rho. The tangential force is mat. You took the total, which is the square root of the sum of the squares, and recognizing also the total is mu mg. And we just put the numbers in and see what we get. So I'm just going to put numbers into this equation right here, and we're going to call that force total is mu mg squared, ma tan, plus mv squared over rho, the quantity squared, and you can find the velocity is 3.056. The tangential acceleration is what's needed to find out the velocity. Again, the velocity is the tangential velocity as it goes around here. As it goes around here, that's the tangential velocity, and that is given by the acceleration in the tangential direction. And so we're just going to say v tan is equal to a tan times time, and you can find the time. The second version of the problem is set up exactly the same, so I'm not going to go through the detail here of how to do that. But what we're looking for here is the coefficient of friction required to fall off if you were given the speed that it takes to fall off. So I was given 3.25 as the speed that it falls off, and you just have to find the coefficient of friction. So it's just a tiny bit different it's set up exactly the same, but they're just a tiny bit different in the numbers. All right. Then the velocity was calculated exactly the same, or the time to fall off was exactly the same type of calculation. Here we get time is equal to 2.167. This next problem is a, if you want to call it, a roller coaster kind of problem. Remember, we did whoop-de-doos and roller coasters. In this case, you had to, we were looking for the normal force, and, whoops, sorry about that. We were looking for the normal force and the force of friction, and then this last question, does he have his foot on the brake or the accelerator? Well, we'll get to that in just a second. But you set all these problems up exactly the same way, and you draw the free body diagram. So I was looking for an accurate free body diagram with the axes, the tangential axis and the normal axis have to be drawn on there. It's helpful to draw the angle there, but then you draw the mg going down, and you need the components of mg, and which are mg sine theta and mg cosine theta. There will be a normal force and a force of friction. So these are going to be the forces in the tangential direction, and these are the forces in the normal direction. And it's important to understand those two directions and those concepts in order to set the problem up and do it correctly. All right, so the first thing you do is take the derivatives of this line, and that we need y dx and d squared y dx, and so I've done that right here. And then we evaluate that at the distance, and this one was 200 meters at x is equal to 200 meters. We resolve that, and we can see that dy dx is 0.32 and d squared y dx is 0.0016. We can now find the next two things, which are theta and rho. And remember, theta is only resolved by taking the slope, or the inverse tan of dy dx. Some people tried to find the slope by looking at this distance, where this was 200 and this was some distance in the y direction, and taking the value there. But remember, we did that in class, and that's an incorrect way of looking at the slope. So the only way to find the slope is to take the derivative. Then we take the, then we plug the numbers into the rho equation, and we can find out the instantaneous radius. Next thing we do is sum the forces in the normal direction and sum the forces in the tangential direction. So in the normal direction, you know, again, recognizing positive normal points in toward the center of rotation. So normal is positive, which means that mg cosine theta is negative, and that's what I'm setting up here. Positive normal minus mg cosine theta is equal to the acceleration, mass times acceleration in the normal direction, which is mv squared over rho. Solving that for the normal force, we get 16,189. Now recognize also that I gave you in the problem the weight of the car. The car weighs 15,000 newtons, so that is my mg. The mass would be the weight divided by gravity. Now, virtually nobody, very, very few people got mixed up on that, so I was very happy to see that. That you know, people were, all of you were very good at discerning the weight versus the mass here, so that's great. Now, the forces of friction, or excuse me, summing the forces in the tangential direction, we do by looking again at the free body diagram. I'll have the mg sine theta going downhill, so that'll be a positive, because positive tangential is in the direction of motion. I drew the force of friction backwards, assuming that the force of friction was slowing him down. But let's resolve that. So if I sum the forces in the normal direction, I get positive mg sine theta minus the force of friction is equal to mass times acceleration. In this case, in this problem, the acceleration was 4 meters per second, and I got the force of friction as a negative number. If force of friction is a negative number, and I drew it going backwards, that means since I resolved it as a negative number, that means the force of friction is actually going downhill. If that's the case, then something is driving the car downhill. If the force of friction is making it accelerate downhill, that means it has to be on the accelerator. He has to have his foot on the gas. So a lot of people got that mixed up. So if the force of friction is pushing you downhill, then that means that something's making it go faster downhill, and that would be your foot is on the accelerator. All right. So that's the conclusion that I got, is that your foot is on the gas. On the next version of the problem, I'm not going to go through this because it's exactly the same, but I had a few, just a couple of values that were different. This one we had the x was equal to 150 and the acceleration was equal to 3. Set it up exactly the same, so you can see the new numbers here. We had a different angle. This one was 13.5. We had a different row of 680. We had a slightly different normal force, setting it up again exactly the same way. Slightly different force of friction, but again it was negative, and that the force of friction was a negative value, and that meant that the conclusion about being on the brake or on the gas was the same. All right, this next one, what we were doing here was going along in this direction, and we're going to throw a rock out of the car, and we're going to try to hit the sign over here. So how to set this problem up, it was recognizing what is the actual and what is the relative. That's always the challenge for students. And so what is actually happening? The car is actually going to go in this direction. The rock is going to start here, and it's actually going to hit the sign. That's the way we understand the problem, is actual is going that way and actual is going that way. The relative is usually the most confusing, and but you recognize dynamics speak in that in the problem it says that if he was standing still, he could throw the rock at 70 feet per second, and he aims it at an angle. So both of those are going to be the relative term. So this is going to be the velocity of the rock relative to the car. So that's why I've set this up. First of all, I have to define my axes and make sure that I have an I and a J defined on the picture someplace so I know. In this case, I also found that distance there of I've taken the square root of the sum of the squares, and that's going to be the distance that the rock actually travels is 58.3 feet. So set this up. Find the actual of the car. We know the car is going to go in the I direction. We know the rock is actually going to go in this direction. So I'm going to say that, but I don't know the magnitude. I know the direction because it's going to, if I do a ratio kind of method of 30 over 58.3 in the I direction, my positive j goes this way, then I have a negative j going this way. So the velocity of the rock actual is going to be 50 over 58.3 in the negative j direction. The relative term is 70, and this one is sine 10, so we got sine 10 in this direction and negative cosine 10 in that direction. Set it up with one equation. That's what I did here. Write the equation, then put all the numbers in the equation, then combine the i's and the j's, and so I'll take that I term and that I term. Whoops, I forgot that. That should be an I right there, so I'll change that on my written page, but that should be a VAI, and then I got the i's and j's there. And then you do the j's. You combine that j term, and the only other j term is over here. Then you usually have a two equations to a known scenario. In this case, we were able to solve for the actual velocity of the rock of 80.38, and we can substitute that into this equation and find the velocity of the car. And that's what we're looking for. The velocity of the car was 29.21. To find the time, we recognize that if we know the actual speed, which is this way, and the actual distance, which is that way, and there's more than one way to find the time, so this isn't the only way. But that's probably kind of the easiest to understand, I believe, is you find the actual distance it's going and the actual speed it's going, and then just divide those and find the time. So s is equal to the velocity times the time. That's the total distance. This is the total speed, and you can find the time. The other version of the problem, the only thing I did was change the angle. So in this case, it's just angle is 15 degrees. Set it up exactly the same way. So I'm not going to go through how the setup is here. I guess for this solution, I did calculate this angle theta or angle alpha. I called it angle alpha as 31 degrees. And did sines and cosines there instead of the ratio method, just so that you can see the slight difference. But all of these things are set up exactly the same. That's set up the same way. You combine terms, and you get velocity of A is 22.45. And the time is, again, slightly different because the distance is going to be the same over here, but the distance is going to be the same right there, but because the velocity of the rock was slightly different, we had a slightly different time, and that was 0.7395. Now the last problem was a very, this was one of the more subtle problems, if you will, is that we're finding out how whether this truck is accelerating too fast to keep the box on the back of the truck, and whether or not it's going to slip off or not, or whether or not it's going to slip off. So anyway, the way we set this up is there's more than one way of approaching these problems, but probably the easiest way to do is to assume it is slipping and then check to see if your assumption was correct. So if you assume that it's slipping, you draw a free body diagram of the box. You recognize that the box is moving in this direction along with the truck. It has an acceleration in that direction, so I'm going to call that direction positive. The only thing that could possibly push the box forward is the force of friction between the box and the bed of the truck. So that's my free body diagram of the box. And I just find out how fast the box could go. The maximum speed or the maximum acceleration of the box is when the force of friction is equal to its maximum, which is in the slip or impending slip condition. And then we find that mu is equal to 0.4, then 3.924 is the maximum acceleration of the box. If I assume that it's slipping, then I have to look at the truck. And the truck acceleration would then be calculated by taking the two forces from the box, which are the force of friction and the normal force, and transfer them equal opposite to the truck. Now the truck only has a 20,000 Newton force to accelerate it. It's also going to accelerate in that direction, but that force of friction is going to slow it down slightly, and I just set that up as 20,000 minus the mu mg from the box is equal to the mass of the truck. And this is where many people made a mistake, is they included both masses in this in the truck only calculation, but it is only the truck, so it has only the 4,000 kilograms for the truck, and then so the truck is accelerating 4.09. Now, how do you know whether, or 4.019? How do you know if it's slipping or not? Well, the best way to look at this thing is that if you look at the scenario, just looking at the picture, the box cannot go faster than the truck. It just can't. It can't accelerate faster than the truck. So when you resolve it, if you get the truck accelerating faster than the box, then you have confirmed your slip condition. And that's what I did down here. Because the acceleration of the truck is greater than the acceleration of the box, the slip condition is confirmed, so I knew that I made the correct assumption. Now, on your test, I did not take off for failing to check this slip condition. But this is a really important concept of checking to see if your assumptions were correct. And so again, this exam I did not take off for that oversight. But in the future, we're going to have to keep that in mind, because that's a really important consideration. Another way to check for the slip condition is to assume non-slip. Now, in the previous page or previous solution, I said I'm going to assume it's going to be slipping. Another way to do it is to check for, or is to assume that it is not slipping. And then you say, if they travel together, that means that they're not slipping. And I can say that if they travel together, I have a 20,000 Newton pushing force. I know that they move together, and then I put both masses in my mass times acceleration equation, and I said that the acceleration, if they travel together, is 4 meters per second squared. And then I have to compare that to the maximum acceleration for the box, which is, again, back to the same kind of approach. The only thing that if I drew the box alone, the only thing that could push it forward would be the force of friction, and I could again go back to the maximum acceleration of the box is 3.914. And then what you do is you compare what I discovered here to here, and what makes more sense. I know that the box cannot accelerate greater than 3.914. If they travel together, they travel at 4 meters per second squared, which means that this is an impossible scenario. I can't go faster, or I can't accelerate greater than my maximum. And so there again, I can assume, or not assume, I conclude that the slip condition is confirmed. So anyway, more than one way to resolve that, and as we go forward, we'll have more problems like this to to prove that it is either slipping or not slipping or some other scenario. Thank you.